Okay, so here's a classic equilibrium problem. A painter is climbing a ladder, which makes an angle of 30 degrees with respect to the ground, and the ladder rests against a wall and the floor. And it says that there's friction on both the wall and the floor. And then the question asks, how high up the ladder can the painter climb without the ladder slipping? So you can imagine that if the painter gets to a certain part, then all of a sudden there's too much, you can think of it as pressure on the top, and it starts to slide down, right? We won't look at pressure. Instead, we'll treat this as an equilibrium problem. The ladder shouldn't move. And so the conditions for equilibrium are, we want sum of the forces to be zero, and we want sum of the torques to be zero. Okay, in order to figure out what the forces are and the torques are, we need two things. We need a free body diagram, and for the torque, we need a rigid body diagram. Okay, in the case of the free body diagram, let's see. On the ladder, you've got the weight of the ladder, which is little m g. You've got the weight of the painter, which is big M g. And then you've got the normal force from the wall, and you've got the normal force from the ground, not to scale. I know the arrows don't look like they're going to cancel, but I just ran out of room. Okay, and then you've got two friction forces. You've got one friction force from the ground, and that points this way. So friction force from the ground, and then your other friction force comes from the wall, and so that's going to be here, and that is friction from the wall. Okay, if we want to turn this into equations, we can. So let's do that. Sum of the forces in the x, that has to be zero for equilibrium, so that should be equal to minus the force of friction from the ground plus the normal force from the wall. Okay, but this can be rewritten as minus mu, given in the problem, times the normal force from the ground plus the normal force from the wall. All of this is zero. Okay, so that's in the x direction. In the y direction, some of the forces in the y, we have the normal force from the ground plus the friction force from the wall. So I'm going to just go ahead and write that in as mu times the normal force from the wall, okay? And then minus the mass of the ladder minus the mass of the man times gravity. All of that also has to equal zero. Okay, so let's just take a quick stock of what we know and what we don't know. Mu is known, but NW and NG, neither one of those is known. And the other thing that we don't have any handle on yet is D, which is what the problem is asking us. So we're going to have to, come up with another equation. Okay, so let's do that. Let's make our rigid body diagram. So rigid body diagram basically means just draw a rigid rod and now say, where do these forces act? Okay, so you've got the weight of the object, the weight of the ladder, so that's little m g, and that is a distance L over 2 away from the pivot point. You may wonder, why am I measuring from there? Like, why measure from here? Why shouldn't I measure from up here? Or why not measure from the center? All of those are perfectly good options. And in fact, if you remember, torque can be calculated about any point. There's no reason why I have to calculate the torque about that particular point, but because the problem asks for a distance from that point, and more particularly, there are two forces that act at that point, so I'll draw those right now. I know that there is friction, which acts here, and the normal force, which acts here. If I choose to calculate the torque about this point, then I don't have to deal with those two forces in my torque equation because their lever arm is zero. I'll draw that into the torque equation and you'll see what I mean, but it's a strategic place to pick to calculate the torque about because you end up including fewer terms. Okay, anyway, I've drawn the normal force to friction, and then also up here we've got normal force from the wall friction from the wall. And then the final thing is the mass of this painter. So I don't know where the painter is, but I'll draw him up here. And this is big mg, and the problem specifies that this distance, the whole distance, is d. Okay, so that is a lot. Let's put it into a torque equation. So if we do that, we have sum of the torques equals, has to be 0 because we're in equilibrium. Okay, let's look at them. So I'm going to write these just for completeness, but they're going to go away. Let's start with these two, right? You've got torque in general. Torque in general is RF sine theta. That's the magnitude of the torque, right? So R is the distance from the pivot to where the force is being exerted. In this case, there is no distance. They're both 0. So I would write like 0 times friction from the ground plus 0 times normal from the ground. They don't really contribute anything, and that's one of the reasons I was saying it was nice to pick the pivot point there. Okay, next let's move to the next force, which is mg. Okay, so the force is mg. Okay, its distance is L over 2. It's the center of mass, right? And then let's see, sine of the angle between. So the angle between R and F. So R points this way, and F points straight down. So that's like this angle, right? But this angle is really, the sine of that angle will be the same as the sine of this angle, right? Now the angle that's given in the problem is 30, but then that makes this angle 60. So this will be mg L over 2 times the sine of 60. Okay. Now the only other thing we need to do is torque's a vector. I got to figure out whether this is positive or negative. And so you just make a choice. You say things that rotate it, say counterclockwise, we'll put a minus sign in front of, and things that rotate it clockwise, we'll put a plus sign in front of. This has a tendency to rotate it counterclockwise, and so I'm going to put a minus sign. You can also use right-hand rule. If you put your fingers in the direction of R, that green arrow I drew, and you fold them down into the force, mg, then what you'll find is that your thumb points out of the page. And so we're calling torque that points out of the page negative. Okay. All right. Next, we've got plus. So the next force is the weight of the man. The analysis is the same, except that we draw a big M, we draw a G, and now instead of an L over 2, we write D, and then it's still sine 60. And then this also wants to rotate it counterclockwise, so I'm going to put a minus sign in front of it. Minus. Okay, big M. So I've got two more torques to consider, and those are these two pieces up here at the end. They're both a distance L away from the pivot point, so I just need to include the forces. The first one is the normal force from the wall, and so we've got normal from the wall times L, because it's L away, and then for the angle here, R goes this way, so the relevant angle is this, but the sine of that angle is the same as the sine of this angle, theta, and that's the same as the angle that the ladder makes with the ground. So I can write there times the sine of 30 degrees. And then last force, I have friction, so I'll put plus friction, so that's mu times the normal from the wall times the distance from the pivot point, the lever arm, which is the length of the ladder, times, now instead of sine 30, this guy, the relevant angle is this smaller piece right here, and so that's 90 minus the other one. So this is going to look like cosine 30 degrees. And both of these, notice I put a plus sign in front of both of them. Both of these want to rotate it clockwise, so I put plus signs in front of both of them. Okay, at this point, the physics is done. It's just algebra soup at this point. Okay, so you'll take this equation and you'll solve for NW and NG. In fact, you don't even really need NG. You'll take NW and you'll punch it into this equation, and you'll do a bunch of fancy algebra, and you will be able to solve for D. D will be some value. I don't really care to do that, to be honest. What I wanted to show you is how to set it up, how to build your torque equation. So what are the big takeaways? The takeaways are: make a free body diagram, make a rigid body diagram. For your free body diagram, write sum of the forces in the x, sum of the forces in the y. If it's in equilibrium, set them all equal to 0. The final piece of solving problems like this is building your torque equation, which requires building your rigid body diagram. And then you just look at the thing, you pick one point, any point, doesn't matter, but it's advantageous to pick points that have forces at them. That way you can ignore the forces in the torque equation. They'll go to 0 like these did. Okay, and then if something wants to rotate it clockwise, put a plus sign in front of it. If it wants to rotate it counterclockwise, put a minus sign in front of it. Okie doke, I will leave it to you to work out the algebra.